Assalamu alaikum dear students. I hope you're all fine by the grace of Almighty Allah. I welcome you all to the 10th lecture of Thermodynamics 2. Lecture 10. The contents of lecture 10 are cyclic heat engines, how to increase thermal efficiency of heat engines, Kelvin Planck statement of second law of thermodynamics, perpetual motion machines of second kind PMM2, Clausius statement of second law of thermodynamics, refrigeration systems and second law of thermodynamics, COP, that is coefficient of performance of refrigerator. So that COP is represented by the subscript R, COP subscript R. Heat pumps, coefficient of performance of heat pump, that is represented by COP with subscript HP. Relation between COP of heat pumps and COP of refrigerator. Coefficient of performance of heat pump relation with coefficient performance of refrigerator. Numerical problem and conceptual questions and answers. So cyclic heat engine. So there are some definitions that we should know initially. So the first definition is, what is a thermal energy reservoir? So the definition of thermal energy reservoir is that it is a hypothetical body with a relatively large heat capacity that can supply or absorb finite amount of heat without undergoing any change in temperature. So you should remember that the temperature of thermal energy reservoir will always remain constant. So the example of thermal energy reservoir can be ocean, river and atmosphere. So let's suppose that you have a huge room, or you are burning a fire in outside your home or in the open atmosphere. So the area or volume of atmosphere can absorb that heat with negligible change in the temperature, or you can understand it by that an ocean contains a huge amount of water. So if you take a bucket or two bucket of water from it, the level of ocean, there will be no change in the level of ocean. So in water and atmosphere, all these are the example of thermal energy reservoir. Or you can say that if you have a warm water bucket, you throw it into the ocean or river, the temperature of the river will remain the same. So ocean, river and atmosphere are the example of thermal energy reservoir. So there are two types of thermal energy reservoir. One is called as source and the other is known as sink. So thermal energy reservoir that is at a higher temperature, so that is represented by TER is the abbreviation of thermal energy reservoir, and capital H is the subscript which represent the higher temperature. So that is known as source. Thermal energy reservoir that supply energy in the form of heat, and TER subscript L is the thermal energy reservoir known as sink. So the temperature of sink is always lower than thermal energy reservoir that is at higher temperature. So sink temperature will be less and source will be greater. So definition of TERL is thermal energy reservoir that absorb energy in the form of heat. So sink will always absorb energy, whereas source will provide heat energy. So you can see a diagram is shown. So the above is the source. So energy is coming out of source and entering into low temperature, that is sink. So TERH is the thermal energy reservoir at higher temperature is known as source. Thermal energy reservoir that is at low temperature is known as sink. And as you know that heat is always transferred from higher temperature to low temperature. That is why the arrow is solid, whereas on the right hand side you can see the dotted line arrow. So the process that are not possible are represented by dotted lines. So as you can know that heat can never flow from low temperature to higher temperature. That is why that is an impossible process. So that is represented by dotted arrow. So heat will always flow from source to sink. So TERH source left hand side and TERL is the low thermal energy reservoir at low temperature, and TERH is the thermal energy reservoir at higher temperature. So the main component of cyclic heat engine is so definition of heat engine is a heat engine is a work producing device. This device convert heat into work. So heat engine is a work producing device and it convert thermal energy into work or heat energy into work. So the example of heat engines are steam power plant, automobiles. So steam power plant, as you know that a high energy, high enthalpy steam. We have a water in a drum. We provide thermal energy into the water, which raise its energy content and enthalpy of the water and convert it into high pressure, high temperature steam. When that steam strike the blade of turbines, the enthalpy content is reduced of the steam and energy is transferred from steam to the blade of the turbines. And these turbines are designed so that these will rotate upon that strike. So that rotational energy is that is connected to these blades are connected to shaft, which is also connected to generator. So generator will convert that mechanical form of energy into electrical energy. So we have supplied heat to the water content. So the heat energy that is in the form of thermal energy is converted into mechanical form of energy, and that mechanical will eventually will be converted to electrical energy. So steam power plant is an example of heat engine. As you know that in automobiles there is an engine and we will supply energy which is in the form of chemical energy. So we will burn the petrol or diesel in the engine or automobile. There is also an engine. So in the piston cylinder arrangement, a mixture of petrol and air is introduced. We will discuss it in detail in the upcoming lecture as well. So there is a mixture of fuel and air, and when there is a combustion, that chemical energy upon combustion will convert into thermal energy or heat energy, and that heat energy will be converted into translation energy or energy utilized to drive the car. So that is a schematic diagram of power plant. So as you know that there is a drum and heat energy is transferred to the boiler and the energy content is raised. High energy, high pressure steam is strike on the turbine blades and low energy, low temperature steam comes out. There is a heat exchanger condenser that extracts the heat from the steam and convert it into liquid, and that is a pump that will pump the water back into the boiler. So you should also remember that symbol of boiler as well. sometimes only symbols or schematic diagrams are drawn and that boiler is not written, so you should remember that the symbol of boiler as well. So from first law of thermodynamics, del sigma q is equal to sigma w, as that is a cyclic, so cyclic heat in cyclic process, so the term u is out. QH minus QL is equal to WT minus WP. So heat addition is on the boiler, heat is added at the boiler, and QL heat is rejected from the condenser or heat exchanger, whereas WT is the power output of turbine and WP is the power input to pump. So as you know that pump utilize power to operate it, we have to supply power, so power is supplied to the system is work done on the system is negative, so WP is negative sign. So QH is kept on the left hand side, whereas all terms are taken to the right hand side, and QH heat of the source is equal to WT minus WP plus QL. That is the relation we have obtained. So as already we have discussed in the detail that we have a source that is a high temperature thermal energy reservoir, and we have a sink that is a low temperature thermal energy reservoir. High energy thermal energy reservoir that is at a high temperature will supply heat in the form that heat is QH, supply heat to heat engine, and some of that thermal energy is converted into work that is represented by W net, whereas rest of the thermal energy is rejected to the sink. So eta thermal, that is the thermal efficiency, eta thermal is equal to output over input. So output is W net, the work that we have obtained from heat engine, that is our output. So output is W net divided by input, that is QH, that is the heat supplied to the heat engine from high temperature thermal energy reservoir. So thermal efficiency is W net is the value of QH minus QL. So we will put the value of W net into the equation, that is QH minus QL divided by QH. So the relation for thermal efficiency comes out to be 1 minus QL over QH. How to increase the thermal efficiency of heat engines? So the relation of thermal efficiency of heat engine is given by thermal efficiency is equal to 1 minus QL divided by QH. We have just derived this relation in the previous slide as well. So if we want to increase the thermal efficiency of heat engine, then there are two methods to increase the thermal efficiency. Number one is by increasing the value of QH. So as you can see, this is a relation, and this for 100% efficiency the value of eta thermal is 1. So the term on the right hand side is reducing the 100% efficiency, so 1 minus QL divided by QH. So the first method to increase the thermal efficiency of heat engine is to increase the value of QH that is in the denominator. So the main goal is to reduce that term that is deducting from 1. So the first way is to increase the value of QH, and the other method is to decrease the value of QL, that is QL is in the numerator whereas QH is in the denominator. So by increasing denominator or by reducing numerator, the thermal efficiency can be increased. So here is a definition of working fluid. A working fluid, a fluid to and from which heat is transferred while undergoing a cyclic process. So a working fluid will be flowing into the cycle and heat will be transferred to and from through the working fluid. Kelvin Planck statement of second law of thermodynamics. Statement of Kelvin Planck statement of second law of thermodynamics. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce net amount of work. So it states that uh, it is impossible for any device. It means it is impossible for any heat engine to operate in between a single energy reservoir. So in the previous slide we have discussed that heat engine always operate between two thermal energy reservoir. A thermal energy reservoir that is at a higher temperature is known as source, whereas a thermal energy reservoir that is at a lower temperature is known as sink. So heat engine receive heat from source and reject heat in the sink. So the Kelvin Planck statement states that it is not possible for a heat engine to work from or receive or reject heat between a single energy reservoir. Second point, it is impossible to construct a heat engine whose all heat energy is supplied into work. So that means that if a heat engine is working for between a single energy reservoir, that means a heat engine is receiving a heat and converting it completely to work. So it is not possible to convert 100% thermal energy into mechanical work. So as we have discussed earlier that thermal energy is a low grade form of energy, so it can never be converted into 100% into mechanical work. So the Kelvin Planck statement also suggests that third point, basically it means that heat being a low grade energy can never be converted into work with 100% efficiency. So there will always be a decrease in the energy while converting thermal energy into a mechanical form of work. Whereas work being high grade form of energy can be completely converted into heat. So let's suppose if you have 100 joule of thermal energy and 100 joule of mechanical work. So if you have Q is equal to 100 joules and W is equal to 100 joules. So if you want to convert 100 joules of thermal energy into mechanical work, that will always be less than, so let's suppose it is you convert 90 joules into mechanical work. Whereas if you have 100 joules of mechanical form of energy, then you can convert it 100% to thermal work, thermal energy. Therefore, second law of thermodynamics is also called as law of degradation of energy. So as you know that the word degradation mean is a thing that is reduced after some time. Reduction, degradation of reduction. So Second law is also known as law of degradation of energy, because there is always a decrease in the energy. So thermal energy is reduced while converting into mechanical form of energy. Thermal energy of any heat engine cannot be 100%, therefore it is always less than 100%. So if you are asked to design a heat engine that has 100% efficiency, so you can never design a heat engine that could have a 100% efficiency, because Kelvin Planck statement suggests that a heat engine will always have energy that will be less than 100%. So if you have the best of the best heat engine, that should have energy or efficiency that is thermal efficiency less than 100%. So this is the limitation of heat engine on the basis of Kelvin Planck statement of second law of thermodynamics. So the limitation that a heat engine cannot have 100% efficiency is because of the Kelvin Planck statement of second law of thermodynamics. Impossibility of having 100% efficient heat engine is not due to friction or other dissipative effect. So as you know that friction, there is always a friction when there is a mechanical displacement or work or motion is involved. So friction usually reduce the efficiency, but here it is suggested that as there is a limitation that heat engine cannot have an efficiency equal to 100%, the efficiency of thermal engine will always be less than 100% as suggested by Kelvin Planck statement. Therefore this limitation is not because of friction or any other dissipative effect. It is the limitation that applies both to the idealized and actual heat engine. As we know that in idealized cases we neglect the effect of friction and other dissipative effect. So in actual heat engine all these effects like frictional effect and other dissipative effect are affecting, but when we are studying or researching, discussing the idealized effect or idealized process, then we neglect the frictional effect. So in the fourth point it is suggested that the limitation is not due to the friction or any other dissipative effect, but this limitation applies to both idealized and actual heat engines. Therefore whenever any machine will absorb heat to produce work, it will radiate some energy to the surrounding. So it is a limitation of Kelvin Planck statement that heat should always be rejected into a low energy thermal reservoir. Perpetual motion machine of second kind, PMM2. So the perpetual motion machine of second kind is, it is a hypothetical machine that violates the Kelvin Planck statement of second law of thermodynamics. So we have already studied the perpetual motion machine of first kind. So first kind was that violates the first law of thermodynamics, and the perpetual motion machine of second kind is the machine that violates the Kelvin Planck statement of second law of thermodynamics. Perpetual motion machine is a machine whose thermal efficiency is 100%. So as you know that it is a hypothetical machine, so it is not a real machine. We only study, we use it in a research purpose or in to study or to understand different aspect. So it is not a real machine, it is a hypothetical machine. So its thermal efficiency can be equal to 100%. So a machine which completely convert heat into work. Perpetual motion machine is a machine that completely convert heat into work. So schematic diagram is, it is a heat source heat source will always have a temperature that is higher, so heat energy flowing from higher temperature to into the perpetual motion machine of second kind, and there is no heat rejection to the lower thermal energy reservoir, and all the heat that is entering into the perpetual motion machine of second kind is converted into mechanical form of energy, or work is reduced from the perpetual motion machine. So now in the schematic diagram, in the term of steam power plant, it is represented here. You can see that in an examination point of view, you may be asked to draw a perpetual motion machine of second kind in the form of steam power plant. So as you can see that a low temperature, high pressure water entered into the boiler. Heat energy from the source is supplied into the boiler that will raise the energy content of the steam, and steam, it will convert liquid water into high pressure high temperature steam, and that steam will strike at the blade of turbine and work will be reduced. So normally you will see a condenser here. So in this schematic diagram they have deleted that portion, a condenser. So basically a condenser is a device that is used to reject the heat into the atmosphere. In the first slide I have already told you atmosphere is also a thermal energy reservoir, as its temperature is lower than the boiler. So atmosphere, in steam power plant, atmosphere will act as a thermal energy reservoir that is at a lower temperature, is also known as sink. So you can see that there is no sink in this diagram. So only heat is supplied to the boiler is converted into turbine. Let's suppose 100 joule of heat is supplied into the boiler. So 100 joule of work is deduced from the turbine, because there is no heat rejection to the atmosphere, and there is a pump. Another schematic diagram is shown that thermal energy reservoir at a higher temperature is giving heat into the heat engine, and there is no heat rejection, and all the heat supplied is converted into the work. As this is an ideal, you have already said that it's a hypothetical machine. So it is a hypothetical machine, that is a schematic diagram, so it is not possible in the real life scenario. So here is a paragraph from a book. So if you are asked to make a perpetual motion machine of second kind by, so you can how you will make a perpetual motion machine of second kind. A heat engine that violates the second law could be made into a perpetual motion machine of second kind by taking the following step. Consider figure 7.11. So that is the figure 7.11, which might be a power plant of a ship. So you will see that in the first slide you have already studied that ocean is also a form of thermal energy reservoir. So now you will see that an amount of heat QL is transferred from ocean to high temperature body by means of heat pump. So you have already studied what is the function of heat pump, or you will be studying heat pumps in an upcoming slide as well. So the function of heat pump is to take heat from low energy reservoir and give heat is ejected at a high temperature. So energy is inserted or work is done on the heat pump when energy is supplied to the heat pump. So energy is heat pump take energy from low energy reservoir and reject it into high temperature reservoir. The work required is W dash and the heat transferred to the high temperature body is QH. Let the same amount of heat be transferred to heat engine that violates Kelvin Planck statement of second law and does an amount of work W is equal to QH. So there are two devices, a heat pump and a heat engine. So the function of heat engine to take energy, high temperature energy is inserted into heat engine and heat engine converted into work and reject the other into the low energy thermal reservoir. So as this heat engine is a perpetual motion machine of second kind, so it will work only on the one thermal energy reservoir. So heat rejected by the heat pump is equal to heat taken into the heat engine. And heat engine, function of heat engine to give out work, so that work is equal to the amount of work that is inserted into the heat pump. So this work is equal to QH minus QL is required to drive heat pump, leaving the net work W net is equal to QL available for driving the ship. Thus we have a perpetual motion machine in the sense that work is done by utilizing freely available sources of energy such as ocean and atmosphere. So in this manner you can devise or theoretically design a perpetual motion machine of second kind. So here in this paragraph or example, we have designed a perpetual motion machine of second kind in which this is a heat engine of a power plant of a ship. So low energy thermal reservoir is an ocean. Clausius statement of second law of thermodynamics. Statement: it is impossible to develop a cyclic device which transfer heat from low temperature to higher temperature without any external energy. So Clausius statement states that it is impossible to develop a cyclic device which transfer heat from lower temperature to higher temperature without any external energy. So this statement suggests that we to eject heat from to take heat from lower temperature and throw it out on the higher temperature side, you have to use some energy. So as you know that heat always travel from high temperature to low temperature. This process is instantaneously. That means by itself. So you don't have to supply any form of energy to direct heat or release heat from higher temperature to lower temperature. But if you want a heat that is at low temperature, let's suppose 10 degrees centigrade, and move it to some higher temperature, let's suppose 25 degrees centigrade, then you will have to supply heat energy. You will have to supply some form of work, energy or work. So you will have to do work on system. Let's suppose you will have to supply, let's suppose, electrical energy. So electrical energy will be supplied to take heat from low energy thermal energy reservoir that is at 10 degrees centigrade to reject it into higher temperature thermal energy reservoir that is at 25 degrees centigrade. So there must be electrical is an example. Mostly we have electrical devices. So I have given example of electrical energy. So there may be another form of energy, but you have to supply some of form of energy, or you have to supply some form of work to take heat from low energy thermal energy reservoir to high temperature thermal energy reservoir. So Clausius statement said that it is impossible to take heat from low thermal energy reservoir and take it out on the high temperature thermal energy reservoir without doing any form of work on it. So second point, Clausius statement is usually used for refrigerator and heat pumps. So as you know that in refrigerator, the temperature of cabinet of the fridge in which evaporator is installed is at very low temperature. That is usually for upper cabinet the temperature is in the minus, because it's a ice cabinet. So the temperature is usually minus 15, minus 12, and the heat is rejected into ambient air. So refrigerator use electrical energy to take heat from low temperature thermal energy reservoir, and that is a cabinet of the fridge is at low temperature and ambient air is a high temperature thermal energy reservoir. Third point, heat always has tendency to move from higher temperature to lower temperature spontaneously, and we want to do converse of that, then we have to supply some form of energy. So that is a schematic diagram of Clausius statement. So it is written that it is impossible to, for any device, cyclic device, it may be heat engine or refrigerator or heat pump, to take heat from low thermal energy reservoir that is operating at a low temperature and reject that heat into high temperature thermal energy reservoir. That is impossible. So we have to supply some form of work, mechanical or electrical, to do this work. Refrigeration system and second law of thermodynamics. Refrigerator. Refrigerator is a device which operates in a cycle and maintains a body at a temperature lower than temperature of the surrounding. So the working fluid in is a refrigerant. So in a refrigerator, the working fluid that is flowing in the tube is a special kind of refrigerant. So the most common refrigeration cycle is a vapor compression refrigeration cycle. So you have already discussed that this vapor compression refrigeration cycle in the previous lecture as well. So we will look it into the in detail. The objective of refrigerator is to maintain cold space at low temperature. So as I have already told you that in refrigerator, let's suppose that is a refrigerator. These are two cabinets, and at the back of the fridge you will see these type of tubes, and there is a compressor. So compressor will increase the pressure and temperature, and high temperature high pressure fluid, that is a special kind of refrigerant, move in the condenser coil. So heat will be rejected to the ambient air. and there is an expansion valve, and this will reduce the pressure and temperature, and the evaporator is installed inside the fridge. So evaporator is also a heat exchanger, so it will take all the heat from the cabinet and move it into the refrigerant, and then this is a cyclic process, so this fluid will move back into the compressor. So the objective of refrigerator is to maintain cold space at low temperature. So low temperature is the inside of the fridge. So this is a schematic diagram of refrigeration system or vapor compression refrigeration cycle. So compressor at the inlet, so the temperature is moderate and pressure is low, so compressor will increase the pressure as well as temperature. These are the condenser coil I have shown here, so they will reject heat into the ambient air. So high heat is rejected into the high temperature or high thermal energy reservoir, that so the temperature will be reduced but the pressure will is at high pressure. Expansion valve will reduce the pressure and temperature, and there is an evaporator, and evaporator will take all the heat from the cabinet of the fridge and increase the temperature of refrigerant, and this is a cyclic process that will go on. Refrigerator, warm environment. So that refrigerator we have to supply heat energy, or we have to perform work on the refrigerator. So usually we will supply energy in the form of electrical energy. Energy will be taken out, cold refrigerator space is at TL. Energy will be taken out from refrigerator space and ejected into the warm environment. That is also a schematic diagram of refrigeration system. So W net plus, so as the direction of arrow is in the opposite direction of heat engine, so W net plus QL is equal to QH. So as we have discussed the thermal efficiency for heat engine, so there the efficiency of refrigeration and heat pump is in the form of coefficient of performance. So it is written as COP and subscript R. So COP of refrigerator is desired effect divided by work input. So it is equal to QL, desired effect is to maintain the low temperature of the refrigerated space, QL, and work input W net is equal to Q. If we move QL on the right hand side, then it will be W net is equal to QH minus QL. So it is written W net is equal to QH minus QL. So COP of refrigerator is QL over QH minus 1, or QL divided by QH minus QL. Heat pump. Heat pump is a device that transfers heat from low temperature to high temperature. It operates on same cycle as the refrigerator but differ in its objective. The objective of heat pump is to maintain a heated space at high temperature. The schematic diagram of heat pump is shown below. So as you can see that the function of heat pump is to take heat from low temperature and eject heat at a high temperature space. So QL is the amount of heat that is taken out from a cold environment, that is at a temperature TL. By doing so, heat pump utilize the energy input. So W net is the amount of work done on heat pump, and QH is the amount of heat that is rejected out in the warm heated space, that is at temperature TH. Therefore, W net plus QL is equal to QH. Coefficient of performance of heat pump is given as desired effect divided by work input. As in the heat pump, the desired effect is to maintain a temperature TH in the warm heated space. Therefore, the coefficient of performance of heat pump is given as QH divided by QH minus QL. QH minus QL is basically the work done or work net. Relation between coefficient of performance of heat pump and coefficient of performance of refrigerator. So the formula for coefficient of performance of heat pump is given as QH divided by QH minus QL, and COP of refrigerator is QL divided by QH minus QL. So you can see the numerator term is different, whereas the denominator term is same for both coefficient of performance of heat pump and refrigerator. So let's suppose COP of heat pump, we denote this as a equation 1, and coefficient of performance of refrigerator as equation 2. So as we subtract both equation, so coefficient of performance of heat pump minus coefficient of performance of refrigerator, then QH divided by QH minus QL minus QL divided by QH minus QL. Therefore, as we solve, then the left hand side, the difference between coefficient of performance of heat pump and refrigerator comes out to be equal to 1. So COP of heat pump is equal to 1 plus coefficient of performance of refrigerator. So according to Clausius statement of second law of thermodynamics, COP can never be infinite. Conceptual question. Electrical appliances, TV, stereo use electric power as input. What happens to the power? Are those heat engines? What does the second law say about those devices? So the answer is most electrical appliances such as TV, VCR, stereo and clock dissipate power in electrical circuits into internal energy. They get warm. Some power goes into light and some power into mechanical energy. The light is absorbed by the room wall, furniture, etc. and the mechanical energy is dissipated by friction. So as you know that in friction, the heat energy is dissipated in the form of friction. So all the power eventually ends up as the internal energy in the room mass of air and other substances. Therefore, the rejected energy in the ambient air is absorbed by the room mass of air. These are not heat engines, just the opposite happens, namely electrical power is turned or converted into internal energy and redistributed by heat transfer. These are irreversible processes. Second conceptual question. Heat engine and pumps or refrigerator are energy conversion devices alternating amounts of energy transfer between Q and W. So either work will be converted into heat or heat will be converted into work. Which conversion direction from heat to work or work to heat is limited and which is unlimited according to second law of thermodynamics? So the work output of heat engine is limited Q to W. You can transform W to Q unlimited. Conceptual question. Ice cube in glass of liquid water will eventually melt and all the water approaches room temperature. Is this a reversible process? Why? There is heat transfer from warmer ambient air to the water as long as there is a temperature difference. Eventually, all the ice will be converted into water as the temperature approaches to each other and there is no more heat transfer. This is a reversible reaction as we cannot make ice cube out of water unless we run a refrigerator, and that requires a work from surrounding which does not leave surrounding unchanged. So the ice will be converted to water, and if we want water to convert back into ice, then we have to provide some energy to an energy device that can transform from water to ice. Numerical problem. A gasoline engine produced 20 horsepower using 35 kilowatt of heat transfer from burning fuel. What is the thermal efficiency and how much power is rejected to the ambient? So you can see that is a heat engine. So QH is the heat injected into heat engine. W out is the work output, or W dot out is the power output, and Q dot L is the heat transfer rate to the low temperature sink, low temperature energy reservoir, or we also call it sink. So we will convert 20 HP 20 horsepower into kilowatt. So 20 horsepower is equal to 14.91 kilowatt. Efficiency of heat engine is given by W dot work output divided by work input, or Q dot H. So efficiency is 0.43. Energy equation. Q dot L is equal to Q dot H minus Q dot out. So 35 minus 14.91 is equal to 20.1 kilowatt. So that is the power rejected to the ambient or low temperature energy reservoir. So QL is equal to 20.1 kilowatt. A refrigerator removes 1.5 kilojoules from cold space using 1 kilojoule work input. How much energy goes into the kitchen and what is its coefficient of performance? So energy equation. QH is equal to W plus QL. QH is equal to 2.5 kilojoule. Formula for coefficient of performance is given by QL divided by W. So you should remember that in books sometimes coefficient of performance is also written by beta symbol. So wherever beta or COP is written, that means the same, that means coefficient of performance. So COP is 1.5. So the back side of the refrigerator has a black grill that heats the kitchen air. Other models have that at the bottom with a fan to drive the air over it. So as you know that is a form of condenser. So you know that before this grill there will be a compressor. So it will compress, and by increasing the pressure, temperature will also increase. So this grill will work as a heat exchanger. So as air moves naturally or forced, convection will occur and the temperature of the refrigerant flowing through these pipes will reduce significantly. Home assignment. All students are advised to go through example problem of each topic discussed in this lecture. So you should go into your textbook and revise and go through example problem of these topics. All students must submit handwritten lecture summary report minimum of 3 pages before the commencement of next lecture. All students are advised to submit hard copies of every assignment and report. All students are advised to prepare previous lecture thoroughly before next class, as there will be a viva or oral answer question session for every student. Thank you.